at the stuff the rest of the stuff that's due Monday here, so let's have a look. Yeah, I'm having problems with YouTube right now, just for those of you online, so I'll hopefully get this stuff sorted out. Okay, so this one, I just want to be sure that you know the difference between the two things, the angle of twist and the maximum shear strain. So one of them is alpha, the other one's beta. So just fill in the top of that alpha and beta and turn it in. And I'll probably just let you figure that one out, okay? So, you know, and there's nothing much to do on that other than write alpha in one of the blanks and beta in the other. And that's on page 18A, that's on the top, so, okay. So one of them's alpha, the other one's beta, and just figure out which one's which and fill them in. That's all I need you to do on that, okay? So, you got any questions on that business? Okay. Okay, 363 is next. So this is one of those things where you can't exceed two values, okay? So 130 megapascals and an angle of twist of 2.063 degrees. Now, you know, this is just uses those two basic formulas, and that's what we're going to be doing in this class, is using those. So, what they are, so you want to do a few things on this. You want to find the moment of inertia, okay, and you always do that. It's a polar moment of inertia. The formula there is pi over 2 times the outer radius to the 4 minus the inner radius to the 4, okay? That's the formula there, and you'll get the moment of inertia. These typically are really small numbers, so 33.7 times 10 to the minus 6, and then I stay in meters on that, so that's meters to the 4. All right, now be a little careful here. You can't use degrees for angles. They've got to be in radians, so that's 0.0360 radians. Okay. And then you've just got the two basic formulas that you use for this stuff is the shear stress is TR over I, and then the angular deformation, you might call it, which I call the twist angle sometimes, is TL over IG, okay? So those are the two things that you are going to work with. And on these particular ones, you just rearrange them. So you're going to have the torsion is what? The shear times I over the radius. And then the torsion is the angle times I times G over the length. Okay. So you just kind of work them like that. And then you can solve for the two torsions. Now you're going to get two of them. So, you know, keep that in mind. These are two independent things that you're solving for. So when you run this torsion, you should get 527. Nope, 567. There we go. And then on this other one here, you should get 527. Okay, so that's how that ought to work. And then what you want to do is pick the limiting value. All right, and so remember, when you're doing design or picking things, you go with the smallest stress and you go with the biggest size. That's the safe way to design things, okay? Okay, so those are just two independent criteria, and you just kind of go through and test them both. So we got any questions on that one? Okay.
Does that mean it's failing at shear at 62,000 and then it's failing at twisting at 48,000?
Yeah,
So
right.
you're just going to say the whole thing is going to fail at 48?
Yeah, basically what we're saying, yeah, right. What we're saying the torsion can't exceed 48,527, because if it does, we're going to have too much twist in the shaft. As soon as you go up to 48,528, you got too much twist in the shaft. So you got to stop when you get to 48,527. That's how I think about it.
Okay.
I just think of having like some torque on there that's just increasing, and you just got to stop at some point.
Okay.
And the point is 48,527.
That's the torsion max allowed.
Yeah. Yeah, and sometimes people get to thinking that the two are somehow connected, and they try and simultaneously solve the shear and the angle equation. That's not how you do this at all, because these are just two independent things that probably have no direct relation to each other. The shear can't go above 130 megapascals, and the angle can't go above 2.063 degrees. So you just test them independently, and then just check your answers against each other. And pick the smallest of the two. All right. All right, then we got one of these angular ones. Okay, so what you want to do on this, there's kind of I use the real systematic way. That's how I like to do it. So I'll sum the torsions and I'll find the reactive torsion at A. Okay, so I've got those 3 applied torsions. I find how the shaft reacts at A. It'll be 11,000 pound-inches. And then what I would do here next is work through the 3 pieces. So I want to work through A to B, and then C to D, and then I got a new load at D, so from there I'll go from D to E. So I'm going to basically work through 3 different columns of calculations. I'm going to find the twist of each section of the shaft. Okay, that's what I'm going to do on this one. All right, so the first one I'll find the torsion from A to C, and that's 11,000 pound-inches. The next one will be -5,000, and the last one will be -2,000. So you just want to go through and work through those. What I'm doing there to solve is I'm finding the reactive torsion over here, and that's 11,000. There we go. And then, then from there you can kind of work through. Now, what I would do here to find these internal torsions, it's just like that normal stress stuff we did before, or axial stress. You cut. And the one thing that's going to be a little different about these is normally you start at the reference point, which in this case is A. You work your way out towards the right. So you get 11,000 going one way and TAC going the, and then you solve for that unknown TAC inside of that shaft, somewhere between A and C. So this number would hold anywhere between A and C. There's one internal torsion in there, which will cause a uniform twisting throughout that, okay? So I went ahead and solved for that. It's just sum of torsions is 0. I work my way from left to right here, so I've got that -11,000 plus TAC, and I solve for TAC. It's 11,000 pound-inches. And then you can do the same thing for TCD and TDE. Okay, like that. And then you solve for those internal torsions, and then once you've got them, what you do is you just figure out for each section of the shaft the angle, TL over IG. So you just calculate those different things up. You've got T, the length is pretty obvious. It's right off the sketch. You can calculate I, it's just pi over 2 r to the 4. And you're given G. So you just run the numbers there, and what you're getting is an angle in radians. Watch your signs because they matter, okay? So you get those different values then and then you just add them all together and you'll get the total angle which I usually convert it back to degrees. You don't have to, but I have a better sense of degrees. I don't have a very good feel for radian measures. Okay. Have you got any questions on that one? Okay. Okay, so that's what those are due Monday as well. Okay. All right, now we're going to finish up some of this stuff on torsion. Not all of it today, but I don't think. But we're going to keep working through this. All right. All right, so let's look at this biaxial stuff again. 620. All right, so you can apply this biaxial stress stuff to torsional shafts. You can apply it to anything really. And if you remember, we went through all this biaxial stuff. It took a good long while. And I kept telling you, well, you use standard design equations to figure out what those original X and Y stresses are. When we did the biaxial stuff, we always assumed that we knew what they were, and now we're getting to some examples of how you figure out what the X and Y stresses are to begin with, okay, with just some of these specific examples. So when you got a shaft in torsion, what you do there is you start with the torsions. Okay, so you've got that torsion on the right. Let's say you find the reactive torsion on the left. Okay, one on the right, one on the left. And from there, and you draw them in. I always like to draw them in. So if I've got the torsion on the right, let's say that's the one that I know, that's the action, so to speak, that's doing that. Well, the one on the left is going to go the other direction, okay, to balance out, because these shafts are in equilibrium. They might be spinning, but they're in then a case of dynamic equilibrium. They're not accelerating, speeding up, or slowing down or anything. They're just going at a constant speed. That would be dynamic equilibrium, I guess. I don't know, but anyway. Okay, so we use statics. We get both torsions. Then you look at the directions of the torsional arrows. It helps if you don't draw them up and over or down and below. If you just draw them on the surface there. So this torsion here on the right would just be going up like that. The reactive would be going down. From there, you can get those translated into shears. Okay, and so the shears act the same direction as the torsions. So this one goes up, that one goes down, the others meet in the corners. Okay, like so. And then the normal stresses in the X and Y directions are 0. So there's your biaxial element. So to get from the torsion to the shear, you just take TR over I to get the number, and then look at the direction of the torsions to get the directions of the shears on the element. Okay. We're good with that? All right, so what we have there is a pure shear element. Everything's shear. There's no normal stress on the X and Y planes. And if that's the case, then we can look at our biaxial equations and look at the stresses at different angles that we might be interested in. And they get quite a bit simplified because the sigma X and Y's are zeros, so they zero out. So you get sigma x1 is just tau xy sine 2 theta, and sigma tau x1 y1 is tau xy cosine 2 theta. And those are on the back of your formula sheet. They're just the biaxial equations, but because those normal stresses zero out, they simplify quite a lot. So they'll often list them as though they're separate equations, but they come right from the biaxial stuff, okay? Okay. And, here's an example of why you might want to look at the stress at a given angle. Sometimes they make hollow shafts by taking a long, thin sort of plate and wrapping it and welding it. You might want to check the stresses on those welds, okay? I was driving a hay swather once, and I had a PTO, and it wasn't a PTO shaft, but it was the drive shaft broke. It got a little exciting there, so you got to see some biaxial stress there real time as that thing was flopping around in the universal joints, and two things flopping around. So, these things will break at funny angles sometimes on account of these biaxial effects. Okay. Yeah, the mechanic told me, yeah, we figured the thing was going to go here in a little bit. And I thanked him for letting me know after the fact. Anyway, okay, so we got that general equation to find the stresses at angles. We've also got the formulas to find the maximums too, because the maximum shear occurs on the 90 and 180 degree angles. It's just the TR over I formula to get the maximum shear. The maximum normal stress then acts 45 degrees off the maximum shear, like we found in biaxial. And you've got one set of tensions, the other set of compressions, and it's equal to TR over I also. Okay. So let's have a look here at some failures for different types of materials. So what I've got here are some materials that I can feel with my hands, so that'll act like materials you might run into on the job when you start working there. So a mild steel is a ductile material. It's stretchy compared to like a cast iron or something, so it's got just a little bit of stretch into it. So what I'll use, and I don't know if I've got this right in your, in your notes directly. I don't think I do. So if you take a mild steel and make a shaft out of it and apply enough torsion to it to break it, how do you suppose it's going to break? Where do you expect that thing to fail? Any guesses? What's that? In the middle? Yeah, what angle? 45? Okay, a 45 would assume what kind of failure?
Shear.
No, normal stress the other way around, okay? See, normal stress is maximum right in the 90 and 180 degree planes. Because in torsion, it's all shear right there. See, that maximum shears are those shears acting on that element just up and down and left and right. So torsion's backwards from pressure vessels. Pressure vessels are all normal stress on those planes. Torsion's shear. Okay. So if this thing's going to shear, what plane now? What do you think?
90.
Yeah, this is, simplest thing in the world, right? It just does that. Okay, I'll just twist it and it goes. But there is a highly technical explanation for why it's doing that. Okay. There we go. It just fell straight across. But see, that's a shear failure is what it is. Okay. So it just shears like that. And that's just straight shear. And what you're doing, you're taking one plane and you're twisting it past the other. That's shear. Okay. Very simple thing. I mean, it's no big deal, but that's really technically what's going on there. Okay. Good? Okay. How about a brittle, granular material? Cast iron, concrete, pretzels,
45.
styrofoam. Yeah, now what kind of failure is a brittle material going to have?
Normal.
Yeah, which one? Compression or tension?
It'll be compression. Well, and tension.
Tension, because brittle materials got grains. The grains don't lap. So when you pull on them, they'll go in tension quicker than compression.
I was just also thinking of pretzel, if I smash it.
Oh, that's true. Yeah, pretzels aren't really known for their structural strength, I guess. But I'm doing the best I can. I got to take something that's familiar. Concrete might be the best example of that. You can push on concrete all day, it doesn't break, but you can't pull on it. Okay. So let's take this thing, and I'm gonna. Okay. So what I'm gonna do. I'll use my right hand. That's on your right. Okay. And that's going to come over the top and down like so. So the left's going to go the other way. So what I've got there is an element like that. You all good? And which way is the shear going to go on this side, up or down?
Down.
Yeah, down because it matches the arrow. This one's going to go up. Yeah, they meet at the corners. All right, now we can do calculations to figure out which side is tension and which side is compression. But there's a visual way you can do it too. It's kind of like vector addition. Add these two here, like vectors. And what are they going to do? They're going to pull that way, aren't they, if I added them like vectors? Mm-hmm. Same thing with these other two. Do that, they'd pull down that way. So there you go. That's tension. Now, what if...
That's the normal stress?
Yeah, right. That's how the normal stress acts. And then if we go with these two now, add those like vectors, that's going to push like that, isn't it? If I add those two like vectors, they'll add up like that. You with me? And same thing with these two. So you can add up adjacent pairs of arrows and you can figure out which side's tension and which side's compression.
Could we have done that previously for the, let's say for the
biaxial stuff?
Biaxial.
It's more complicated because you got shears and you got different magnitudes. These have the same magnitude, so it's pretty straight up. It's a little more complicated on the full-blown biaxial stuff. So that's why I just do the numbers. You can visualize it if you want, but it's a little trickier doing it. It's hard to explain. So
visually it'll still work out, but as far as getting specific numbers, then that's what it is. Yeah. Okay.
And the other thing is, this class is pretty small, but there's people online too. If I got to explain this to 30 people at a time, it's a heck of a lot easier for me to just find the angle, plug it in, and get the answer. It's simpler for me. Sure. Visually, you can do it. There's ways to do it. It's not really not that hard. You just kind of align the stresses on the angled element as near as you can to the XY stresses. Is really all you're doing. But it can be a little hard to verbalize it and explain it to them. Okay, so we'll just kind of pull on over like that. Bang. Okay, now this thing's a little stretchy, so it kind of did fail at a clean 45. And you can see that 45 better on the other side, which will be a little deceptive because I'm turning it around now. But there's that nice 45. And the rest of it was kind of like a spiral fracture. They talk about that with bones, actually. Sometimes people kind of twist their leg and such. But so you can actually see it better. I want to keep it this way so we'll match. Okay, see how that tension went that way? And that way. That's a tensile failure. Right? Right. So I forgot to bring the pretzels, but there's a nice 45 failure on a pretzel. So it's the same sort of stress there, although that one I guess I did different, didn't I? Because it went the other direction.
It's going to be larger.
Yeah, I know, it is. This is the way you can get yourself a free drink.
If I can snap this at a 45-degree angle, you get the next drink.
Yeah. Well, you're either going to get something for free or weird looks. I don't know what people failing pretzels is a little weird. Okay, so, but that's the best I got. I don't know. I used to be able to get this styrofoam pretty cheap, but I can't get it anymore. Okay, then we've got the last one is a thin-walled tube failure. And often, they save money. They make hollow torsional members there. What kind of failure are we going to have with that? If it's thin-walled.
Or I would imagine, well, because I've done this before, so I'm...
That's funny. Everyone's done this. Yeah, it's just kind of, I don't know why people do this.
No, not smashing.
Yeah. I'm not talking compressive failure on your head here. We're talking twisting failure.
Twisted. 40.
Yeah.
Yeah,
Emphasis is on.
It's a shear, it's almost like 90.
I don't know if it's going to be a shear. Thin walled. How about the thin part? What happens to thin stuff? What do they weaken? Thin things.
Compression.
Yeah, compression. Okay. And okay, so I guess I'm doing this backwards. So what I did on the actual slides, but we'll do that. So we'll do that. Now there's meat. So compression ought to come that way, right? And tension ought to go that way. You all with me there? Okay. Let's roll that over the top. See how that follows? And that totally screwed up. Oh, I went the wrong way. I rolled this over the top and I'm showing it the other way. Anyway, let's just look at the slide. There we go. That one was done properly. So let's see, it's coming. Yeah. I drew my arrows wrong. Initially, I didn't turn my hands the way the arrows went. There we go. So that's what I did. Actually, I rolled my right hand over the top. Yeah, okay. There we go. So that went like that. Crushed it in, okay. You all good with that? So like that. So got a 45 degree failure, not quite 45. These ends kind of work things a little bit. We're good? Okay. All right. So much for the 4 minutes of looking at things. Now we got to do 50 minutes of calculations. Cursive engineering.
So you did have a map of calculations on 611, but that's a different.
Yeah, we skipped that. That's just kind of a little bit redundant there. 6:30. All right, so if we want to figure out the maximum and minimum stresses here, or maximum stresses, I should say, maximum shear and maximum compressive and tensile, and then also find the stresses on that particular element. Let's see if we can do that. Show each of these stresses on a sketch. So why don't you, let's see, why don't you put the reactive torsion in there on your sketch to start with, okay?
Oh, on the main sketch?
Yeah, up top there. Yeah, up top. Okay. So we doing that? And then I got kip feet there, so this would be the same. What? That's 5,000 pound-feet times 12 would be 60,000 pound-inches. I want to get these into pounds and inches because I've got my shaft dimensions in inches. So to get things to match, I like to get when I'm in English, I like to get my torsions into pound inches. Okay, like so. So you all good with what I did there? It's not, horribly complicated. The reaction just goes the opposite direction of the applied. That's all. Okay. All right, now why don't you fill out those other two sketches, and we don't have time, we don't have numbers yet, but get the directions. Okay, what are the stresses acting on that element, and which stresses are acting on this element?
The first one we're adding in the shear.
Yeah, just figure out what kind of stress to put on them and get them pointing the right directions. I would start with the one that's on the top for you. It's on the left for me. So figure out what stress goes on that thing and get it pointing in the right directions. This is a thing, school's so different than work. I mean, school's 10% visualizing this stuff and 90% running the numbers, but works the other way around. You got to kind of figure out what the problem's going to be. You'll spend a fair amount of time just thinking about that. You CEMs, you spend a fair amount of time learning, right, what you're going to apply, with estimating and things like that, which is good. Okay, so that first sketch is shear, right? Is there normal stress on the first one?
I'm sorry?
Is there any normal stress on this first one that has shear?
If it's shear, then that's right.
No, this one won't. Normal. These torsional things are just pure shear and then pure normal. So there's no normal on the shear sketch. There's no shear on the normal sketch. The first one's all shear. The second one's all normal.
Oh, right, yeah.
Yeah, that's all I'm saying. Okay. All right. So which way's the one on the right going, up or down?
Oh.
Yeah, it matches this guy. So that's doing that. That's doing that. So that goes up. This one goes down. The other two meet in the corners, right? Now we don't know the numbers yet, but that's what the arrows are going to do. And then have a look at that and then transfer those arrows in your mind, kind of take them on over to the diamond there, okay? The 45-degree diamond. What are they going to do to that?
Is it because we don't know what we're made out of? We can't figure out.
Oh, we can. We'll crunch the numbers. I just want to visualize it first, and then we'll run the numbers.
Oh, I mean, because I can visualize doing one side, but I don't know.
Yeah, but if one's tension, the other's compression. Because you just got to reduce the processing. All right. So we get tensions going that way, compressions going the other way. We good with that? Any questions on that? And there's no shear on these planes. So these are principal planes. Okay? So that's what's going to happen there, okay? And then we just run the numbers, TR over I. Okay? And they're plus or minus because they're tau max. 60,000 times 4 over 402. Yeah, I already calculated I for you there. So it's 597. Okay. So the shears look like that. They're all 597, all the magnitudes are equal. And see, that's the same magnitude as the normal stress. They're all the same. And I think I've got that on your formula sheet somewhere, something to that effect. Formula 98. Tau max is sigma max is tau xy is tr over I. It's formula 98, I think. So all that stuff numerically is equal. So that's just 597. And that is also what the normal stress is, the maximum normal stress. All right. Now the shears you kind of have to draw visually. You got to look at those applied torsions and get the arrows going in the proper direction. The normal stress stuff, you could do it numerically too. You know, you could do sigma max. You could either do it visually like we just did, or you can just use this formula. This is the general normal stress formula, tau xy sine 2 theta. What we had on our shear sketch was whatever the heck that is, 597. See, that's a positive shear right there on our reference plane. So what that means is if you do this general normal stress formula, sigma x1 y1 is tau xy sine 2 theta, you put positive 597 in for tau xy. And if you plug 45 in there, 2 times 45 is 90. So plus 597 times sine 90 is plus 597. So what that's telling me is, as I was able to do visually, on the 45-degree plane right there, I've got a positive 597. I've also got one going that way. Okay. And then the other maximum normal stress X on the 135-degree plane, so positive 597, that's tau xy, times sine of 2 times 135, sine of 270, negative 597. It's going that way, okay? So you can do them visually, or you can actually run the numbers on them if you're not comfortable doing them visually. Either way is fine, okay? Okay. So that's what you get for the sketches. And then you can also find the stress on the 35-degree plane there. You just plug the numbers in. I mean, it's not, you're just doing the, remember these formulas, they're shorter formulas, but they're just biaxial formulas, that's all. So sigma x1 is tau xy sine 2 theta. And then tau x1 y1 is tau xy cosine 2 theta, and that's on the back. So you just go ahead and run the numbers, okay? And you'll get sigma x1 35 is plus 561, sigma x1 125 is minus 561, and then the shear is plus 204 on the 35-degree plane. Okay. Doing all right with that? And you can make a sketch out of it. You got the normal stress on the 35-degree plane is positive. 90 degrees off of that, it's negative. And then the shear on the 35-degree plane is positive also. So something like that. And you can see that the normal stresses pretty well match the 45-degree plane. No surprise there, right? I mean, as far as which direction they go and that sort of thing. Doing all right with that? So I'll get you a couple of these for Wednesday, 281, 282. I think that's it's the 28th, isn't it?
Wednesday the 28th.
Yeah, thanks. There we go. Okay.